Greetings everyone. So today is our last live session of the course, and we'll mostly solve the problems associated with this circuits first, and then we will try to recap the problems from all the sections, all the previously taught subject lectures from the professor. Like we will start with the wave function problem, a problem on the wave function, and then move to the Schottky contact, and then to the metal oxide capacitance, and finally end with the MOSFET and the circuit analysis in that. Okay, so let us start today's live session. So as I said, we will start with the circuit problems, which we did previously. We solved the small signal analysis. We saw how the small signal model can be obtained for any two-port network, okay, where we used a black box representation and went through the Taylor series expansion of that function and said that we want the amplifier to operate in the linear region. Okay, so all those were the assumptions for the small signal model that we obtained for the two-port network. Okay, so now in this problem we have been given a MOSFET. Okay, a MOSFET is given to us, and we have been told that the MOSFET is in saturation and the current source is ideal. Okay, so this current source over here is ideal current source, and GM is 1 millisiemens, while the output impedance is 10 kilo ohm, and the RS, that is the source resistance associated with this circuit, or sorry, with this MOSFET is 1 kilo ohm. So we have been told to find the small signal voltage gain of this configuration which we have been provided with. Okay, so if we now look into the problem in our hand, we have to first see how does a current source behave when we are going for this small signal analysis. Okay, so the current signal is open, so it acts as an open source. Okay, likewise we have seen the what I can say, the voltage source, the DC voltage source, we replaced it with the ground, and similarly the current source is replaced by a open source. Okay, it is open circuit, not open source, sorry. I am basically dealing with the source load, so that's why I said there is this source load RS which is attached to the source side of this MOSFET, N-type MOSFET, which is given to us. Okay, and it has some output output voltage that we require to find out, and on top of that we have some output impedance of 10 kilo ohm. Okay, we have this 10 kilo ohm output impedance. Okay, so now if I consider this node to be Vx, okay, let's say it is this is node X and this is node Y. Now as we know that the current, if this is the current Ix which is flowing from into this node X, the same current should flow out of this node, okay, Y. But input current, let me write it down, the input current at node X is 0. So what does it imply? So therefore, to obey the KCL rule, therefore to obey the KCL, output current at node y must be also 0. Okay, so it means that the current Iy and Ix, they both are 0, and you can say that if there is current in the circuit, which that is only flowing in this part. Okay, so if I draw now this small signal model for this, it will simply be like this. If this is my n-type MOSFET, this is my V out. Okay, this is my RS is gone. Okay, because there is no current in there flowing through the RS, so RS is gone. So this is a good problem in hand that has been provided to us. So RS is gone. Now we have only V. Okay, so it is simple. What is the gain for this? So this is ideal. We do not have to consider the what we can say, the channel length modulation. So R naught will not be there. So the magnitude is simply Gm times RL, which is the load resistance. So Gm is 1 millisiemens, so it is 10 to the power of minus 3 times RL. RL is 10 kilo ohm. Okay, so it's 10 into 10 to the power of 3, so it is simply 10. Okay, so V out by V in magnitude is simply 10. So let's go back and check the options. Okay, so option B is the correct option to select. Now it says that in changing, okay, so we have to change something. So in question 1, if the value of RS is 3 kilo ohm, magnitude of small signal gain will be, and after changing RS, the MOSFET does not leave the saturation. Okay, so there are these conditions which have been provided to us. So if we change the RS, what is going to happen with gain? Okay, so if we change the RS, what is going to happen? But we drew this model, okay, this small signal model, and we have seen that by using this KCL, that there is no current flowing through the RS. Okay, so since no current is flowing through the RS, no current flows through RS, hence it does not come into the picture when we get the gain. Okay, so you can clearly see, therefore the gain is independent of RS. Okay, so we will select the option D. So the gain is independent of RS. Okay, as simple as it gets. Now moving to other problem. Okay, so now this problem at hand, it has the two MOSFETs of different types. So be careful about these kind of problems. So it is NFET, and the other type over here is P type. So it is P type, okay, and it is N type, okay, okay. So one among them is P type and the other is N type. Now, if we draw the small signal equivalent for these, for let us draw for the M2, okay. So M2, this is the gate which is grounded, and since this is a P type, this is our drain terminal, okay. This is our drain terminal for P type. So this is VSG2 times GM2, and it is connected to the ground, okay. So this is our source of P type, okay, and it is also the source of N type, okay, and it is the current flowing through this is simply GM1 times VGS1, okay, VGS1. So this gate is connected with V in, okay. So this gate is connected with V in, and we are measuring the voltage at this node V out, and to this we have a RD connected, and as we know the DC source has to be grounded. So this is our small signal equivalent model for the schematic shown over here, okay. So now let us do some mathematical manipulations. The currents, now let's calculate the currents. This G, since this is a single, you can say a branch, and in this the current GM1, sorry, GM1 VGS1 has to be equal to GM2 times VSG2, okay. So what is this VGS1, okay? VGS1 is simply V in minus Vs. So let's say this S of N is equal to S of P is simply equal to S, okay. So it is Vs GM2 times Vs, okay. So it is simply GM1 V in is equal to GM1 plus GM2 times Vs, okay. Also, the current flowing through this resistor is simply uh, equal to the current flowing over here, okay. So for the second equation, so let me write it as equation 1. So in order to obtain the second option equation, we say the current flowing is simply 0 minus V out by RD, it is simple KCL, is simply equal to GM2 times VSG2. VSG2 is Vs, okay. Or you can simply say that Vs is simply, in terms of V out, it is GM2 times RD. Okay. So let's be specific. You can clearly see that the units are being satisfied over here, okay. GM2 times, most of the times what students do is they make silly mistakes while solving the circuit problems, okay. So this is a small check. This GM has units of Siemens. This is inverse of the resistance, okay. Let's look it like that, okay. And this RD has the units of ohm, and this GM has the units of Siemens. So overall this quantity in the denominator is unitless, okay, and the quantity thus has the unit of voltage, okay. So this is a small check while calculating these circuit while solving these small signal analysis problems, okay. So you can even say that whenever you are feeling that you might be solving some problem wrong, you may be doing something wrong in that problem, the small check is always the dimensional analysis, okay. So you can always do the dimensional analysis. So this is GM2 times Vs. So we will use equation 2 use 2 in 1. Okay, so it will become gm1v in is simply equal to gm1 plus gm2 times v out minus v out by gm2 rd. Okay, so v out by v in is simply now v out by v in is simply minus gm1 gm2 rd divided by gm1 plus gm. Okay, so the magnitude will simply be, so let's calculate these values first. gm1 is 1 and gm2 is also 1. rd is 10 kilo ohms, so it is 10 to the power of minus 3 times 10 to the power of minus 3 times 10 kilo ohms, so it is 10 into 10 to the power of 3. gm1 plus gm2 is 10 to the power of minus 3 times 2. Okay, as simple as it gets. So this cancels with this goes with this, so it is simply minus 5. So V out or V in is minus 5, or magnitude of V out or V in is simply 5. Okay, so the option A is the correct option to go with. So we will be selecting option A for this problem. Now moving to other problem, which is related to the circuit analysis as well. So it says that, okay, so it says that we have a circuit in hand with two MOSFETs connected to it, and we have to consider a circuit shown with RD. This RD is equal to 20K. Okay, and Kn is this conduction parameter which has been given to us. It's 0.1 milliampere per volt square. The threshold voltage is simply 0.8. We have to ignore the channel length modulation, and if V1 is equal to 5 volts and V2 is 0, what is the output voltage? So this is a nice problem. So what we will see is, for this problem, V1 is 5, okay, and V2 is 0 volts. Okay, so if V2 is 0 volts, what does it imply? V2 is applied over here and source is grounded. Okay, so it implies that VGS2 is 0. Okay, so if VGS2 is 0, it is simply less than this VT value. Okay, so it is simply less than the threshold voltage of the MOSFET. So it implies that M2 is in off state. Okay, so M2 is in off state. Okay, got it? So the MOSFET M2 is in off state. So whole of the current IR, it comes from this and goes into this. We have this branch is carrying no current. Okay, so this branch is carrying no current, and IR is simply now flowing. If you use the KCL, is simply flowing into this branch, which is this. Okay, IR is simply equal to ID 1, and you can clearly see that VGS will be there's some 5 minus 0.8, which will be simply 4.2. And today first order, you can say, if we consider this 5 volt voltage which is being getting dropped across this resistor now and across this MOSFET, you can clearly see that this VDS will be less than the we can say this VGS minus VT. But let's do the complete analysis. Okay, let's not use that approximation. Okay, so what we will do is we will use the what we are having the in hand is we are simply now having this RD, which is connected to this 5 volt VDD equal to 5 volts, and we just have this MOSFET M1 with current ID1 flowing through it, and this is V0. Okay, and this is our V1, and this is connected to the ground. Okay, yes. So it is simply if we use the KCL at this node, it is 5 minus V0 by RD. This is the current IR that we were speaking of, is simply equal to Kn times 2 times VGS minus VT. VGS is V1 minus VT times VD. VD is simply V0. Okay, VDS is this across this. Okay, so it is simply V0 minus V0 squared. Okay, so let's solve for this. Okay, using the value of RD to be 20k. Okay, so it is let's insert some slides. So it is simply 5 minus V0. Kn is having the value of 0.1 milliampere per volt square, so it is 0.1 into 10 to the power of minus 3 times RD is 20k, is 20 into 10 to the power of 3, 2 times VGS is 5 minus VT was 0.8 times V0 minus V0 squared. Okay, so it is, this will go with this, so it's 2 times this thing, so it is simply 5 minus V0 is 2 times 8.4 times V0 minus V0 squared. Okay, so it is simply 2 times V0 square minus 17.8 V0 plus 5 is equal to 0, or simply V0 square minus, it is 8.9, simply V0 plus 2.5 is equal to 0. So what we will obtain is, we will obtain a quadratic equation in V0, which is simply minus b by 8 is 8.9. So let me calculate it. It cannot be plus because output voltage V0 cannot be greater than this value, so it is plus minus. So let me write it down first. 2. So let us use the calculator to calculate it. So it is 2, 9. Okay, so it is coming out to be equal to plus minus 8.32. So plus value cannot be used because V0 cannot be greater than the supply voltage. Sorry, where is it? It cannot be greater than 5. So it is simply less than 5, and it is 8.9. Simply 8.9 minus 8.32 divided by 2. So it is 0.29. So A0 is simply 0.29 volts. Okay, so this is the value of the V0 we obtained. Okay, so we have obtained the value of the V naught to be equal to 0.29. So the option C is the correct option to go with. Okay, now moving to other problem, which is this question 4. Acha, if V1, sorry, if V1 is 0 volt, okay, and V2 is 5 volt, what is the output voltage? Okay, so I guess it will be the same one and the same thing, because both the transistors are identical. Okay, so this is no, there is no uh, funda in doing this. Okay, no, what has happened? Where is this problem? Okay, so now, okay, so that's, I guess that's it on the circuit side. Okay, so we have covered all the problems that were associated with the small signal analysis. Now what we will do is we will try to recap a bit. So this is, there's wave function. This is about the wave function problem, where we have seen that in an infinite potential well, the potential, the wave function outside the well has to be zero, and which are the, we have to look that in graphs a list of the properties are violated. Okay, in graphs A and D. Okay, clearly you can say this, if you can look at this A and look at this D, it is a continuous function. Okay, and its derivative is also continuous. Okay, so you can clearly say that for the infinite potential well case, for this its derivative is continuous and the function itself is continuous, so as a result none of the properties are violated for these. However, for other case, like you can see that there is this property violation. Okay, this function does not have this derivative continuity at this point. Okay, so now let's move to other problem which is associated with the effective mass. Okay, this is just a brief recap of the things that we have been doing in the course. So it is, which of the following explains the relevance of the effective mass? Okay, relevance of the effective mass being negative for some particles in solid state physics. Okay, you must have heard that for the holes we are having negative effective mass. Okay, so this is commonly, you must have commonly heard these kind of terms. Okay, so this has to something do with the mathematical manipulation that we use. So it says that we have been given four options, that the effective mass being negative indicates that the particle's behavior is unconventional and deviates from the standard free particle model. So this is absolutely weird. Okay, the particle behavior is not unconventional, it is just that the behavior will be opposite to that of the electronic behavior. Okay, so the phenomenon of negative mass is still a subject of ongoing research, and this is also absurd. So negative effective mass implies that the particle experiences an attractive force towards the regions of higher potential absolutely, leading to a unique electronic behavior. Okay, so this is what we are looking for. Okay, because what happens is that the negative mass, what does negative effective mass imply? Negative effective mass implies that actually it implies that the particle we are talking about, the particle we are talking about, sorry, I don't know what is happening with this, we are talking about are we are talking about, so since this is singular, is whole. Okay, so it simply means, you must have seen the conduction band minima, so it looks like this. Okay, and the valence band maxima, looks like somewhat like this. And this is a direct band gap material. Okay, I have drawn a direct band gap material. Okay, this is our K, this is our E. Okay, for the time being, consider everything to be this is not symmetric. I have not drawn it purposely to be non-symmetric. Okay, so you can clearly see for this kind of a curvature, okay, you will get a positive effective mass. Okay, positive value for second derivative. Okay, and for this you will get negative. Okay, so that's all. That is all they can say crux of these two graphs. So this is just a mathematical way of representing how the electronic and hole masses are opposite in sign. Okay, that is positive and that is negative. Okay, so the particle in this region is known by the name of hole, and its behavior is completely opposite to that of hole. Like for example, if I apply a positive bias over here and negative bias over here, the electrons will move in this direction. Okay, but the holes will move in this direction. Okay, so that's all. Okay, so the electronic behavior, because of this negative sign, you can say, so for the understanding kind of a thing, because of negative thing, okay, because of this curvature being having this negative over here, it experiences a force which is opposite to that of the electronic motion. Okay, electrons, like for example, they will go to the right, the holes will go to the left. Okay, so as simple as it gets. So why I drew this non-symmetric, you can say, or across this x and y, is because I wanted to show something. So if this is my k, this is a one dimensional, basically we are drawing a three-dimensional quantity in 1D. Okay, so we have to choose some plane. Okay, we are choosing some planes and drawing the energy band diagram, or energy band structure rather, I would say, because this is not an energy band diagram, this is an energy band structure. Energy band diagram means the variation of energy with x. Okay, that is the position along the device, let's say, that is channel length, let's say. Okay, so but this energy band structure means that we are drawing it with respect to the reciprocal lattice vector. Okay, so it is in the reciprocal space. Okay, so this energy band structure, so I drew it asymmetric because the effective mass can be anisotropic. Okay, by anisotropic I mean that in this direction we will be having one kind of a curvature, and in this direction we have having other kind of a curvature. You can clearly see I have drawn this curve like this. It is like this, and this is more steep. This is less steep, and this is you can say this is more steep, and this is less steep. Okay, so what happens is, if I try to fit the parabola in this region, okay, it will be like this. Okay, so this will give me one effective mass. Okay, this will be having one effective mass, and if I fit a parabola in this region, okay, I will be getting some other second effective mass. Okay, so it depends on the direction of the orientation. So for example, if I am orienting a material in, let's say, x direction, you must have heard the planes that once I taught you in the, I guess in the third lecture, that the atomic density for different planes of the silicon. Okay, one plane had different number of atoms and other plane had, let's say, different number of atoms. So due to that we had different atomic density in every plane. So that's what I am talking about. So apart from having different atomic densities, we can have different effective masses because the curvature along that path will be different. So if we orient the device in this direction, we will get one kind of a transport, that is, we will get one kind of response of the electrons. And if we orient the this, you can say, the material in this orientation, we will get the different response to the electric field. Okay, so this is all because we are fitting the parabola. Okay, this is an approximation that we are using. We are using the parabolic approximation for the energy band minimas, that is CBM, and for the valence band maximas, and we are saying that now they, since the curvature is different in two different directions, we will get different effective masses, and because of having different effective masses in two different directions, we will get different electronic transport, okay, and hole transport as well. So this is a simple concept that one should remember, that a material can be anisotropic in nature, okay. It is not necessary that all the effective mass in all its directions will be same. The effective mass can be different, okay. So that's all the crux of this statement that I made. And also the electronic and the whole motion is opposite, okay. That's what we wanted to say, that if we apply an electric field, if due to the electric field electrons are moving to right, the holes will move to the left, okay. That is simple concept. If holes move to the positive to negative, how can we say that negative effective mass experience an attractive force? Okay, so negative effective mass implies that the particle experience attractive force towards the region of higher potential, leading to a unique electronic behavior. Okay, so what it is saying, Mr. Rama is saying something. So if holes move from positive to negative, uh, how can we say negative effective mass experiences an attractive force towards a region of higher potential? Okay, so let me recalculate this thing what we have said over here. Okay, so this is our electronic motion. Electrons will move towards the right and higher potential. uh, Okay, this is what we mean. I guess you must have seen that you have seen the energy band diagram. Okay, we say that the electrons roll down the hill. Okay, it's in that sense. Okay, so electrons roll down the hill. So when you say that electrons are moving in this direction, so this is basically associated with the field itself. You say that holes will move in this direction. Okay, that's what it means. Higher potential kind of a thing. Okay, so the profile motion is completely opposite to that of the electron. Okay, the what is acting as a barrier to the electrons will not be barrier to the holes. Okay, so it's completely opposite motion. Okay, so that's what we mean by this. So I guess this is the correct interpretation for this, that electrons, since electrons roll down the hill, the holes will go up the hill. Okay, so that's the opposite analogy of this thing. Okay, did you got it? Okay, so uh, I guess that is most of the explanation that I wanted to provide about the effective mass. But still, if you have any doubt about this thing, we can have a discussion, more discussion on this even online. That is through the email. Okay, you are always welcome to ask me questions over the email, and I will be happy to answer the queries. And this is what I think, what would exactly mean by this down the hill and up the hill kind of a concept. Okay, so what is actually acting as a behavior for this? So this thing what I had drawn, I have drawn over here. This is simply the electric field like this. Okay, so the electric field is like this. Okay, so this is our electric field. So that's what I have drawn over here. So the holes will move in the direction of the electric field. Okay, so let's not get confused with this. So I shouldn't have wrote it like this thing only. Okay, so I should have drawn it like this as well. If this is my, you can say this is some interface of the metal, and this is the interface of the semiconductor, and this is my oxide kind of a thing. Okay, so this kind of analogy is there only. Okay, so the electrons will move down the hill and the holes will move up the hill. Okay, so this is that kind of analogy in terms of the potential. Okay, so okay, there is some other problem associated with the effective mass, I didn't know. Okay, but I guess this is the mathematical relation that we need to use. Yes, it is that we have to consider the energy dispersion relation for a charge carrier in a periodic crystal, which is given by 2 sine square k, and we have to calculate the effective mass. Okay, so this is another kind of a problem which has been provided to us, which is actually dealing with the effect. We what we saw previously is that we used the parabolic approximation for the the relation between the E and the K was the parabola. Okay, that E is some function of K square. Okay, but now in this case it is some function of sine square K. Okay, so it is simple that this m star will simply be h square by d square E by dk square. Okay, so what we are doing now is we have to derivate this thing. De by dk is simply 2 into 2 sine k times cos k. So d square E by dk square is simply 4 times, so it is so let me write it like this: 2 times sine 2 k इसका derivative, okay, d by dk, okay, because 2 times sine k cos k is sine 2k, so it is simply 4 times cos 2k, okay, which is d square E by dk square. Okay, so m star is simply h bar square by 4 times cos 2k. So the option B is the correct option to go with. So just this was some mathematical problem associated with the effective mass. So I guess, I'm sorry, I have to sip some water. Okay, so now moving to other problem which is associated with the illumination. Okay, that whenever we illuminate the light, I guess we have done some problem kind of some kind of, I guess, in the fifth or sixth lecture we did this kind of a problem where we had this some kind of a light illumination, but let's just try to recap the same concept using some other problem. That if we have this intrinsic semiconductor with the concentration of 10 to the power 10, now we dope it with donor impurities. So if we dope it with the donor impurities, what happens is now there will be excess electronic concentration. So let me write down the first intrinsic carrier concentration is simply 10 to the power of 10 per centimeter cube. Doping is done by using the donors, which is 10 to the power of 15 per centimeter cube, or so the whole concentration will simply be Ni square by Nd, which is 10 to the power of 20 by 10 to the power of 15 is simply equal to 10 to the power of 5. Okay, so you have seen this kind of problem. Okay, so let me look into the EF0 minus EFI. Okay, so EF0 minus EFI in this case is simply KT ln of Nd by Ni. Okay, so it's simply 0.025. So because it has been given to us 25 millivolts, ln of Nd is 10 to the power of 15 and Ni is 10 to the power of 10, so it is 10 to the power of 5, and let us calculate this value. It is simply 0.025 into this number, which is ln of 10 to the power of 5 is 0.288. Okay, so it's 0.288 volts. Okay, now what we are doing is, now this doped semiconductor is irradiated with the some light which is generating the photons at the rate which is 10 to the power of 20 photons per second, such that each photon impinging on the semiconductor leads to the generation of one electron hole pair. During illumination, the Fermi level of holes is located at EFP, and given the thermal voltage, the minority carrier lifetime of the holes is this. So the value of EF0 minus EFP needs to be found out. Okay, so this EF0 is the Fermi level. Okay, after doping. So let me write it like this. Let me show you what it looks like. So since it is a n-type and it has been doped 10 to the power of 15, EF0 will lie above the EFI. Okay, so that's what we have to draw. Okay, and this will be our EV. Okay, so this is what we have found out. Okay, this is what we have found out. Now, by irradiating this semiconductor bar with the light, we are generating one electron hole pair for the each photon. Okay, so we have this generation rate, and because of this now we will be having the uh, increase in the both the minority carriers and the majority carriers, but the majority carrier increase won't be that significant. Let's look into this generation rate first. Okay, generation rate is simply G is simply delta P by delta tau P. Okay, because how much you will generate from this, it depends on the you can say on the generation rate as well as the minority carrier lifetimes. Okay, so the delta P is simply generation rate times the minority carrier lifetime. So it is generation rate is this 10 to the power of 20. Okay, and the minority carrier lifetime is tau p is 10 to the power of minus 6. Okay, so it is of the order of 10 to the power of 14. Okay, per cubic centimeter. Can you see a significant change? Okay, initially it was just 10 to the power of 5, now it is 10 to the power of 14. So yeah, this effective hole concentration has increased a lot. Okay, so the effective hole concentration has increased. Okay, now it is delta P plus the original P which we had when we doped the semiconductor. So delta P is a lot, it is 10 to the power of 14, and this P is simply 10 to the power of 5. So you can approximately write it to be equal to 10 to the power of 14. Okay, so this illumination of or irradiating of the light head has significantly altered the Fermi level in the the quasi Fermi level, we can say now, for the holes. Okay, so now the if I find or if I look into the difference of the quasi Fermi level of this EFI minus the quasi Fermi level of the holes, it will simply be KT ln of n effective. Okay, n effective of holes. Okay, by Ni. Okay, which is simply now 0.025 times ln of 10 to the power of 14 by 10 to the power of 10. So it is simply 0.0259 times ln of 4. So ln of 10 to the power of 4 is 9.2 into 0.025. It's 0.0, sorry. Okay, okay, so that the good thing has happened. Okay, so it is 0.23 in general. Okay, so now this is EFI minus EFP, and this is EF0 minus EFI, but we need to find out EF0 minus EFP. So what we can do is we can add, let me name it 2, add, we can add 1 and 2. So it is simply EF0 minus EFI plus EFI minus EFP is simply 0.288 plus 0.2. So it is simply EF0 minus EFP is 0.518 electron volts to be specific. Okay, so this is the difference between the Fermi level that we obtained when we had doped the semiconductor n type, and they now when we are illuminating the material. So this is just the two difference between the two quasi Fermi levels. Okay, so now moving to other problem. Okay, so let's move to other problem which is associated with it's metal semiconductor short key contact. So these kind of problems are good because we always start with the Poisson equation for these. Okay, we try to solve for the electric fields and the built-in potentials. Okay, for these kind of problems. So they just start from the right from the basics. So an doped semiconductor having a dopant concentration varying as, so the dopant concentration is varying exponentially. Okay, and it is given to be equal to n of x is simply n0 times exponential of minus ax, where x is the I can say the dimension, or the I can say the coordinate along the one of the direction. Okay, which is the channel length. Okay, let's say, so is used to form the metal semiconductor Schottky contact. The junction of the metal semiconductor Schottky contact is located at x equal to 0 and extends up to the 2 by a. So it is between, so the junction is between x equal to 0 to x equal to 2 by a. The semiconductor has a permittivity of epsilon s. Q is the electronic charge, and we have to assume the full depletion approximation. From that we have to find out the this built-in potential expression. Okay, so the depletion width, simply, since the depletion region extends from 0 to 2 by a, the depletion width is simply xt is 2 by a. Okay, so this is the depletion width. Okay, now let's solve for the field. dE by dx is simply rho by as. Okay, now rho, now this E is simply, if I integrate it, is simply 1 by Es, which is the permittivity of this semiconductor, is simply rho dx. Okay, so the E is the electric field, 1 by Es. Rho is simply q times this thing nx. Okay, q times nx. So it is simply q times nx is n0 exponential of minus ax dx. Okay, so it is simply q times n naught by es exponential of minus x minus ax by minus a plus c. Okay, or simply the field expression is minus q times n0 by es times a into exponential of minus ax plus c. Okay, so this is the expression for the electric field. Okay, so the electric field expression we got, but there are some conditions on it. Okay, so the depletion region ends at 2 by a, so the electric field Don't we need the limits? Yes, yes, absolutely, absolutely. So that's what we are doing. I did the integration without the limits. Now I have added the constant term c for this. Okay, that's why I have added the constant term c for this. Okay, so now we will put the limits on this the same expression. I did it, you can say I did it purposely like this. Okay, so that we can get the insights that the electric field at the edge of the depletion region has to go to zero. Okay, so you can see that at x equal to 2 by a, the electric field has to be equal to 0. Okay, there is no charge inside this bulb. Okay, or inside the bulb beyond the depletion region. Okay, actually there will be field, but let's not go into that. Okay, so say that this depletion, there will be zero electric field inside the region because there is no depletion region after 2 by a. Okay, at 2 by a, the electric field must go to zero because there is no charge that is inside the bulb where we have to terminate this electric field. Okay, so since now we have no electric field after the depletion region, neglecting the Debye length. Okay, so let's not get into those concepts at this stage. Okay, so neglecting everything, so the electric field is 0 at 2 by a, so it simply means what we obtained over here, minus q times m naught, okay, by es times a, exponential of minus a by 2 by a. So it is simply this a and this a will go, so this plus c. So this is the purpose of using the definite integral. So c is the constant which we have obtained now, simply equal to q times n naught epsilon s. Okay, had we put the limit, okay, there is other thing. Let me first calculate this. E to the power of minus 2. Okay, this is our electric field now. Therefore the electric field is simply minus q times n naught epsilon s a times exponential of minus ax minus e to the power of minus 2. Okay, so also had I calculated the if we had to, let's say, if I had to calculate the electric field in the region only, okay, not calculate its positional variation inside the depletion region, I would have just put the limit from the 0 to okay, 0 to VB, what you can say, this thing 0 to 2 by a. Okay, 0 to 2 by a. So what that had given me, that would have given me the, if we integrate the electric field like that, now it would give me the VBI. Okay, that's the built-in potential that we are going to calculate in the upcoming slide. Oh, sorry, upcoming module of this problem. Okay, so that's why we have obtained the positional variation of this field, and you can clearly see that when this x is equal to 0, at x equal to 0, that's at the junction, the field will be maximum. Okay, at ms junction. Okay, you can validate this from this expression, and at x equal to minus 2 by a, this will now go to 0. Okay, so this is a boundary value consistent problem that we have obtained. Okay, it is consistent with the values that we should obtain for the metal semiconductor junction electric field. So this is one check we can always do for any problem. Okay, so the electric field we have obtained. Now if we integrate this electric field, this minus d phi by dx, okay, if I now integrate it with respect to the x, is E is simply can say this expression over here. Let me not write it again. So if I integrate it, I will get the value of the d phi, this phi value. Okay, so let me get the value of the phi first, which is phi as a function of position, which simply is q times n naught, okay, epsilon s a, integral of this minus eax minus 2 times dx. Okay, Now we have to get the positional variation. Okay, so we have to get how does this potential vary with respect to the change in the when we move from x equal to 0, that is the metal semiconductor junction, to the depletion width. How does it vary? So it is simply, so q times n naught by ESA is simply, if I integrate this thing, it is simply now EA exponential of minus x minus a, so it is minus e2 x, okay, plus c, again using the definite integral. Okay, now in order to obtain this constant term c, we do not need this constant term c. Okay, I do not need it because I know two things. Okay, which two things I know? I know that this built-in potential is the difference between the potential at the depletion width minus the potential at the metal semiconductor junction. Okay, so let us, in order to not obtain, or in order to, why should we obtain this c? Because it has nothing to do in the difference. Okay, so I will simply subtract 2. Okay, what I will obtain is, I will obtain the phi bi value, that is built-in potential value, which is simply es, okay, okay, times e to the power of simply minus a x is 2 by a minus a, okay, minus e 2 by a, minus of minus, this thing will be plus 1 by a. Okay, so it is simply, this is also has a. Okay, so it is simply q times n naught epsilon s a square e to the power of minus 2 minus times 2 times e to the power of minus 2 plus 1. So it is 1 minus 3 e to the power minus 2. So it is e to the power of minus 3 times 3 minus 1.85. Okay, have I done something wrong? 2 by a is minus 2. Okay, so okay, so from this we have obtained the value of the a to be this number. Okay, this is the value of the a that we were required to find out. Okay, so it is simply this number. Yes, so this is e to the power of minus 2, 2 times minus 2. So let me write it again, let me recheck it. E to the power of minus 2, e to the power of minus 2 times 3 minus 1 is 0.593. Okay, so this value is 0.593. Okay, this is the value of this. Okay, so yes, there are no options to this problem. Okay, so any value between, what has happened to this? Okay, so any value between 0.58 to 0.6 would have worked to us. Okay, now moving to other problem, which is associated with the MOSCAP. Okay, the MOSCAP, we have done a lot. Now I guess it has electric field lines always. Okay, there is some question about electric field on positive and on negative. I don't believe we have a opposite charge in the metal semiconductor depletion. Then how does electric field line still exist? uh, what are you trying to infer? Mr. Ramaya, why isn't there an opposite charge in the metal semiconductor junction depletion? Okay, can you
So in a
unmute?
depletion, we'll have only one kind of charge, right?
Okay, so metal is also there, na? Metal is in contact with the depletion, this semiconductor. Okay,
Okay, electrons in the metal.
Yes, yes, absolutely. You always have that. Whenever you draw this PN junction, you have the same image for the MS junction as well. Okay, but the thing is, the depletion region in case of a metal is very, very, very thin because it's sea of electrons. It has a electrons in, you can say, infinite number of electrons, not infinite, basically it is the Avogadro's number, so it has lot of electrons. Okay, so you never draw this depletion region in the metal side, although there will be depletion in the metal side. Okay, there will be
Okay.
depletion in the metal side. That's what I was talking about, this Debye lengths, or you can say this, there is other term I don't remember at this particular time. Okay, so you have this charges terminating from the metal to the semiconductor. There will be charge in the metal side, there will be charge in the semiconductor, and as a result of that thing you will be having an electric field. Okay,
Okay. Clear.
so okay, so this is a MOSCAP problem. I guess we have done a lot of MOSCAP problems, so let us recap. Okay, so this CV curve is for this MOSCAP with an area of 100 micrometers by 100 micrometers, and we have this p doped semiconductor with an intrinsic error concentration of 10 to the power of 10 and dopant concentration of 10 to the power of 14. The CV curve is given the thermal voltage to be equal to 25, and vacuum permittivity is this. The relative permittivity of the semiconductor has a value that is approximately equal to this. Okay, we have to find the relative permittivity of the semiconductor. Yeah, that's a nice thing. Okay, so I guess we have not done any such problem till now. Okay, yes, I don't think so that we have done any such problem. Okay, so the oxide capacitance from this in the accumulation region is simply, this is the oxide capacitance, and this will be simply equal to 2 picofarad. This is 2, and this is simply 2 picofarad. Okay, and the capacitance, effective capacitance at this thing is the effective capacitance, which will be a series combination of the oxide capacitance and the depletion capacitance. Okay, let me close this so that the screen will be a bit large. Okay, so the effective capacitance is simply, this is 0, this is 0.1, this is 0.2, this is 0.3 picofarad. Okay, this is 1.1, this is 0.2, this is zero point 0.3. Okay, so it is 0.3 picofarad. Absolutely. So now what we can do is, do I need to find, yes, I need to find the depletion capacitance. So for that I need to look into the phi f. Phi f is simply phi t ln of Vt ln of Na by Ni, Na by Ni, and area is, let's get that at the, okay, so Vt is 25 milli ln of Na. Na is, I guess 10 to the power 14. Yes, it is 10 to the power of 14. Ni is 10 to the power of 10. So it is simply 0.23. This we did a few seconds ago. That ln of 10 to the power of 4 is times this 25 is 0.23. Okay. Now the effective capacitance is simply 1 by C ox plus 1 by C depletion. Okay. Or C, this is 1 by C ox is simply, this is simply 1 by 2 picofarad plus 1 by C dep is effective capacitance, or simply C dep is simply 2 minus 0.3, yes, divide into 2 into 0.3 is zero point 0.6, its inverse, so it's simply 0.35 picofarad. So this is the depletion capacitance, okay, that we found out. Now this is the depletion capacitance per unit area. So the depletion, this is total depletion capacitance. Now the per unit area is C dep by A, and it is simply given by Q times epsilon S Na by 2 times phi f. Okay, the depletion width, we have considered the surface potential to be pinned at psi s equal to 2 phi f. Okay, that's the classical definition for the surface potential pinning. Okay, so this is our now if I square this thing, it will be c depth square by area square times 2 times phi f by q times na is simply epsilon naught times the relative permittivity. Let me replace it by k. Okay, this is k. So C depth is the depletion capacitance. It is 0.35 pico 10 to the power of minus 12 whole squared times 2 times phi f. Phi f is 0.23. 2 times 0.23. Area is 100 micro. 100 micro is 10 to the power of minus 4. So it is 10 to the power of minus 4 centimeter square. Okay, so it is simply 10 to the power of minus 4 centimeter square minus 4. So it has to be squared. Q is 1.6 into 10 to the power of minus 19. Na is 10 to the power of 40. Okay, it is 8.85 into 10 to the power of minus 14 times the K. Now let's try to solve for this. It's a huge thing. Okay, minus 24, so minus 8. So K. So the value of K comes out to be approximately equal to 3.9. Okay, so this is the relative, this is the value of the relative permittivity that we obtain. Okay, okay. So now, okay, this is what we required to find out. Okay, yes, that's what it was required. 3.98. Okay. Now moving to other problem, it says that we have to consider. Okay, we have not consider anything. We do not have to consider anything. Okay, we have a designer. Okay, a designer wants your device. Okay, a designer wants your device to behave like this. That you are having a discharging a capacitor is attached to us in a PCB and it is discharging from 3 volt to 1 volt, and he wants the discharge of the capacitance to happen through two different methods, and first is the exponential discharge and other is the linear discharge. Okay, so it is recommended to clearly read the conditions for the MOSFET in saturation, linear and deep triode and cutoff regions to solve the next two questions. For exponential discharge, let's say if you have a mobility of this and oxide capacitance of this, W by L of this, what is the gate voltage applied? Okay, so it is simple. So if we want this exponential discharge through a capacitor, it is simple. We have to have a resistor connected with the capacitor in series. Okay, if we have a RC, we will have a exponential decay of the charge. Okay, so it's as simple as that. So for exponential discharge, MOSFET has to behave as a resistor. Okay, okay. So when does it happen? It happens when we are having this MOSFET in the triode region, and this is basically it is in non-saturation region. Okay, so for that the resistance will simply be mu times C ox W over L VGS minus VTH. Okay, as simple as it gets. Simple. So the resistance value is simply 1 by mu is 1000, which is 10 to the power of 3 centimeter square, times 0.5 micro 6 times VGS minus VTH. VGS minus VTH is 1 volt, I guess. Yes, it is 1. Okay, so it is simply 10 to the power minus 3. It goes above, it's 0.5, so it's 200 by VGS minus 1. So we need to have the exponential decay. Okay, so the voltage with respect to time has to decay. Okay, that is at voltage at time equal to 0 will decay with time like this. This is a simple equation that you have derived. This is V0. Now V of 0 according to this problem is 3 and V of t is at some t is 1. Okay, so it is V of 0 is 3 volts and V of some t1 is 1 volt. Okay, because we are having this exponential discharge. Okay, so it is simply Vt1 by V0 is simply 1 by 3 is simply e to the power of minus t by r. Okay, t by tau is actually. Okay, so it is r is simply equal to t by c ln of 3. Yes, ln of 3, 1 by 3. Yes, it's correct. So it is simply t by c. Okay, uh, t by c is t is 50 microseconds, so it is simply 50. C is what we require to find is r is 200 by VGS minus 1. VGS minus 1. T is 50 microsecond. C is 1 microfarad. 1 microfarad. 1 of this thing and this thing will go. This will go with this. So it's 4 times ln of 3 plus 1. It is 4 times ln of 3 plus 1 is VGS. So let us 4 times ln of 3 plus 1 is 5.39. So the V value of VGS is simply 5.39 volts. So this for this much amount of gate bias, we can have the this will act as a resistor. So for the linear discharge, it simply means that the MOSFET has to behave as a current sink. Okay, the current then there will be only the MOSFET has to operate in the saturation region. Okay, so for current sink. Okay, it is simple. It has to behave as a current source. Okay, for current sink, MOSFET has to be biased in saturation. Okay, so it simply means that the current is simply I times C dVc by dt. Okay, the current I is the saturation current of the MOSFET is simply mu n. Oh, I don't know what has happened to this. It's crashing. I don't know why. Sorry for this. Okay, in saturation it crashed. I'm sorry for this. So the current is I C dVc by dt. That is the change in the capacitor voltage with respect to time. So the I is the saturation current. Saturation current is simply mu n times C ox W over L by 2 VGS minus VTH whole square. Okay, C times TVC is the, can say it is delta V or delta T. Okay, simple as it gets. Okay, so now if I use the values for all these things, 1 millisecond, okay, it is 1 millisecond. Okay, charge is 1 millisecond. W by L is W by L is 10. Okay, W by L is 10. So it is simply VGS is VTH plus 2 times C delta V by mu n C ox W over L into delta T under root, sorry, under root. Okay, so it is simply coming out to be equal to VTH. VTH I guess was 1 volt for this. Yes, it is 1 volt. VTH is 1 plus 2 into C. C is the capacitance value, which was some microfarad. So it's okay. So it's 1 microfarad. So it's 2 into 10 to the power of minus 6. And delta V is 3 minus 1 volt, which is 2. Okay. So it's 2. Mu n is mobility, and it is, I guess, 1000. Yes. So it's 1000 times 0.5 into 10 to the power of minus 6 into W by L was 10. Delta T is 1 millisecond. Okay. Yes, it's 1 millisecond. So it is, let me calculate the value for this thing. So let me calculate it. So it is simply 1.89. So it's VG is equal to 1.89. Okay, you must have seen that I have not written VGS less than VT. Okay, because VGS cannot be negative. Okay, if it would have been negative, then we would have got the condition that VGS is less than VT. Okay, which is not possible. Okay, VGS cannot be less than VT for the MOSFET to behave in the saturation region. Okay, now let's move to other problem, which, okay, so you must have seen the IDVD curve. Okay, uh, in order for the MOSFET to behave as a resistor, when do you get the linear relation between the I and the V? Okay, it is only in the triode region or the deep triode or the non-saturation region. Okay, because now you want the exponential discharge. Okay, if you want the exponential discharge of a capacitor, how can it happen? You have heard, you have derived in the network analysis, in the, you can say in your, I guess even in the 11th or 12th standards, that if we consider take a resistor in series with a capacitor, we will have a exponential decay of the charge. Okay, so that's what we have done in this problem. So in the when the MOSFET is operated in the, you can say in the non-saturation deep triode region, it behaves like a resistor. Okay, it is okay. Okay, unmute,
Sir,
that's
is
much
the
better.
linear mode and sir, is the linear mode and the deep triad both the same?
uh, Actually, there is this confusion, or this, you can say, uh, ambiguity in the terminology. That's why I always use non-saturation. Okay, I say the
Okay.
non-saturation, then the saturation. Okay, and in between those non-saturation and saturation regions we have a region where the transition is occurring between this saturation and non-saturation and the saturation region, and in that region none of the models is valid. Okay, I guess in one of the lectures I showed you how does this qi, the inversion charge, vary. Okay, in one region the inversion charge was increasing exponentially. Okay, and then after that it kind of a linearized. Okay, then we saw that how can this happen, that first of all the inversion charge is increasing exponentially, and then after that it is kind of a becoming a linear function of the gate bias. So whenever you are transitioning from the exponential, mathematically consider the mathematics part over here, when you are transitioning from the exponential to the let's say linear function, there has to be some region, okay, where there is this transition happening between this exponential and the linear, and in that transition region both of these functions are valid. Okay, so that region is the region between the non-saturation and the saturation region. So the more perfect thing will be that in the early stages of the non-saturation region, early stages of the non-saturation region, the MOSFET will behave as a resistor. Okay, let's say few millivolts, for example. If you must have heard the sub-threshold region kind of a thing. Okay, in that region, the sub-threshold region kind of a thing, the MOSFET will be having the resistive behavior. Okay, it's not always true that there will be the characteristics that will be linear in the sub-threshold region as well. For the, I'm talking about novel devices. Okay, considering the futuristic devices, in those devices sometimes you get very high leakages. Okay, and the current just saturates at a point, or let's say for example 10 to the power of minus 5 microamps per micrometer. Okay, and it is continuously remaining constant to a value, let's say from zero point 0.1 volt to zero point 0.3 volts. Okay, so this can also happen. Okay, so that region we can say it is cut off completely, we will say that region to be cut off, but in a broader term we will say it is the non-saturation region. Okay, so that's one thing, but you have to check a region where the variation of the current with respect to the drain bias is linear. Okay, where this id is changing linearly, kind of its linear relation, y equal to mx kind of a relation between the two. Okay, mx plus c. So in that region we will say that the MOSFET will behave like a resistor only. Okay,
Okay.
okay, so okay, so I guess we will move to this problem. Okay, so now let us say that two identical MOSFETs are connected in this fashion. Which of the following statements is true? Okay, we have to comment about the region of the operation of these MOSFETs. Okay, first of all, the MOSFET M1 and M2 are connected, and let us assume that both the MOSFETs have threshold voltage less than 5. Okay, less than 5. VT is less than 5. Let us assume this. Okay, yeah, which is always true. Okay, VT will not be greater than 5 considering non-power devices. If we consider the power devices like GaN HEMTs, or can say these LGAS HEMTs, they might have 5 volt threshold voltage. Okay, so we are talking about the simple silicon devices. Okay, and I don't think so that they will be having 5 volts of this threshold voltage considering the particular technology or the present technology that we are using. Okay, so let's assume that both are in saturation. So this is simple. Assume both M1 and M2 are in saturation. Okay, so what does it give us? It will simply give us that the ID1, since they are in series, ID1 is simply equal to ID2, and ID1 is, let's say it is beta by 2, ID1 is VGS1. Okay, VGS1 minus VTH. VTH is threshold voltage is same for the both. Okay, VT is simply beta by 2 VGS2 minus VT. VGS1 is simply 3 minus Vx minus, it is 3 minus Vx minus Vt whole square is equal to VGS2 is 3 minus Vt whole square. So this is only possible when Vx is equal to 0. Okay. So if Vx is 0, what does it mean? It means if Vx is 0, it means VDS2 is 0. Okay, which is not possible. If VDS2 is 0, but we have assumed that the MOSFET is in saturation, it would mean that this VGS2 minus VT is it is it is not possible for us to have to both the MOSFETs to be in saturation, because this VDS2 is 0. Okay, we don't have this VGS minus VTH be greater than this value. Okay, so what we do is now is we say that one of the MOSFET is in saturation and other MOSFET is in the linear region. Okay, so if I assume that M1 is in saturation and M2 is in linear, what would happen? Okay, so if VDS1, okay, assume that VDS1 is simply VDS1 is simply 5 minus Vx. Okay, 5 minus Vx, and VGS1, okay, VGS1 is simply 3 minus Vx. Okay, it is 3 minus Vx. Okay, it's simple. Okay, so VDS1 is always greater than VGS1 minus VT, but there is one assumption. Assumption is that assume VT is 1 volt, let's say. Okay, we have not been given any information about the VT. Okay, so if I consider this VT to be less than this 1 volt, that although it won't matter over here, because this 5 minus Vx is greater, always greater than 3 minus Vx minus something. Okay, unless Vt is negative, which is not possible for this case. Okay, for the n-type MOSFET, Vt will not be negative. Okay, it is not possible to have as the negative voltage considering these scenarios. Okay, so this is also always true. Okay, so the assumption that M1 is in saturation is a good assumption. Okay, M1 is in saturation is a good assumption to start with. Okay, is a good assumption, and it is true also, na. Okay, so now let's assume the B2, the M2 MOSFET is in linear region. Okay, because it was not in saturation, because VGS minus VT was not less than VDS value. Okay, or we can say that VDS2 came out to be equal to 0 and VGS1 had some value and VT also had some value, so it was not possible to have this VG less than this value. So it simply meant that the MOSFET M1 was not in saturation, because this VGS1 minus VT, it for this you can say for the saturation had to be less than VDS2, or VGS2 has to be less than VTA. So this is contradictory. Okay, this is contradictory statement. If VGS2 is less than VT, it would mean that the transistor is not on only, na. Okay, so this is contradictory. Okay, contra. Okay, so it is simple. The M2 cannot be in the saturation. Okay, so M2 has to be in linear region now. So the M2 is in linear region. Okay, so now if I equate the currents for both, so beta by 2 is 3 minus Vx minus Vt, that is we have assumed the M1 in saturation. Okay, or this M2 is a linear. So it is VGS minus VT. VGS1 is 3 minus Vx minus Vt, 3 minus Vx simply. Okay, VGS2 we have to calculate. Okay, so it is VGS2. So VGS2 is simply 3 minus Vt. Okay, 3 minus Vt times Vx minus Vx square by, so this beta and beta will go, and assuming this Vt to be equal to 1 volt, this is 2 minus Vx whole square is 2 times Vx minus Vx square by 2. So this gives us the value of the Vx to be, let me use the calculator for this. So Vx cannot be greater than 3. Okay, that's the first thing. Okay, because we have applied the voltage VGS to be equal to 3. Okay, so Vx cannot be greater than that, otherwise it will not be in the desired range of operation. Okay, so what we obtain is Vx is 0.845 volts. So which is reasonable assumption for our case. Oh, because M1 will now be in for this bias, clearly this Vx for this Vx less than this thing, this is greater 0.84, it will be some 4.9 approximately, it will be greater than this 3 minus 0.84 is 2.9 minus, it will be greater than 1.9 approximately. Okay, and similarly this VGS for this VGS minus VT is 2 is less than VDS, which is this VDS1 and VDS2 is simply Vx is point this thing. Okay, so what we have obtained is that this MOSFET, one of the MOSFET operates, M1 operates in this saturation and M2 operates in the linear region. Okay, I guess there is, yes, there is one option. M2 operates in the linear region and M1 operates in the saturation region for this case. Okay, so I guess that's it from my side. So, and that is all I had to teach today. So if you have any question, you can unmute yourself, because this is, I guess, this is our last session. And even after this session, if you have some queries, you can always email me. So if you have any question, please unmute.
Sir, I have a doubt regarding assignment 12.
Assignment 12. Okay.
Yes, sir.
Okay.
So
Has that
there I
been?
feel that
Okay. Okay.
yes, sir, it's already answers are already released.
Okay. Okay.
The deadline is over.
Okay. So can you please brief me about that problem?
Yes, sir. So
Okay.
the fourth question, it asks us to select all the states that contribute in conduction mechanism in amorphous materials.
Okay. 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 So it's assignment 12, na?
And they have provided that,
Okay.
yes, assignment 12.
Mm-hmm.
And they have given the options as extended energy states, deep states, tail states, and all of the above.
Okay.
And the answer they have provided is extended energy states and tail states.
Okay.
But sir in the lectures had mentioned that deep states also contribute in the conduction mechanism. So the answer should be all of the above in that case,
Okay. So
because we
so
have
if
hopping conduction.
yes, I am getting your point. So you can raise that in the forum, because the problem with us being TAs is that we cannot control the forum, or we cannot even see this assignment solutions. Okay, I
Okay.
I have no, I can say I have no authority to change any answer. Okay, so you
Okay,
just
sir.
write.
Actually, I had raised the issue in the forum 3 days
Okay,
back itself, but I
if
didn't get
there is
any
no
reply.
response, just email to the professor itself. Nah, tell
Okay, okay.
him that I guess, sir, there is some issue with this problem, and you have taught us in the class that it should be like this. then please look into
Okay.
this. And he will ask one of the TAs, which are the official TAs for uploading the assignments and the solutions. They will just look
Okay.
into that. Okay.
Actually, there are
So,
3 such questions in the same assignment.
oh,
Yeah,
so if you
which I
feel
feel that needs to be evaluated.
you just can you just provide me the question numbers as well? I will look into those
Yeah.
question numbers. Okay.
Fourth question, fifth
Wait
question,
a second. Wait a
and
second. Wait a second.
okay,
Fourth question, fifth,
fifth question,
and
and then eighth question.
okay. So eighth question. So you are saying that the options they have provided, the solutions they are wrong. Okay.
Yes,
So
yes.
you can just email me also these questions. And I guess you have emailed me once. I will reply to that email only. Nah, huh? Okay, it's fine. I guess I have your email address with me. Yeah. So I will.
Okay,
If I find that their solutions are correct, or if your solution is correct, I will just let you know. Okay. I will just solve the
okay,
problem in the evening, and I will let you know.
okay,
Okay.
okay.
Meanwhile, you can also, if you feel that there is
Actually, they are
some.
just theoretical questions, sir.
Okay. Yeah, yeah, I know. That's why I never touched that assignment. Nah. That
Okay,
assignment 12, it's all theoretical questions. Okay.
yes,
So,
sir.
if you have any other query, you are always welcome to ask me or email. I will be available
Sure,
and
sir.
everything. Okay. So,
Okay.
thank you for joining. Okay.
Thank you for teaching us, sir.
Okay. Thank you. Thank you.
Thank you.
So let's end this session. Thank you, everyone. Thank you for joining.